In this tutorial, you will learn to use Epsilon Wave Drag. Epsilon Wave Drag is a filter that allows you to perform a profile drag breakdown, and in particular to extract the wave drag component from the profile drag. So, let's take a look at that. Basically, Epsilon Wave Drag is a filter that can be applied directly on Epsilon aerodata. What allows you is to extract the shockwave and the viscous components on the entire flow field. So, for example, let's say that you have an entire 2D or 3D domain. You can separate the entire domain and retain the part where the shockwave appears as well as its own wake, as well as the viscous part, even if you have shockwave or not. And this can be applied either to the entire domain, 2D or 3D, but also to a slice of the domain. In this case, what we are seeing is the wake of a rectangular wing that you can actually download in our website. It's a 3D transonic case. And this is the wake at the survey plane. And again, this wake contains in red the viscous part, in green the wake of the shockwave. So this filter allows you to separate. In green here shows the part of the wake where the shockwave wake lies. And here in red you have the part of the wake that includes only the viscous part. So, in order to understand how we achieve these operations, we have to understand first what is information that Epsilon aerodata provides me. So, concerning the grid, Epsilon aerodata generates a BTK unstructured grid. So this is the geometry that it will be taken by the filter in order to slice, if I want to just analyze a slice of the wake, or to analyze the entire domain. Also, it will retain some point data, in particular energy or drag densities. These are the criteria used to identify the different parts of the wake, so this data must be retained. And the last part is some field data, in particular the transformation matrix, because this information will allow me to properly position the survey plane in order that the survey plane be always normal to the upstream flow direction. We'll talk about that later on. So let's see what we have inside Epsilon Wave Drags. That is what's happening on the background inside ParaView when you execute this filter. The first thing that happens, and this is optional, we will understand that later on in the practical part, is that we can perform a slice of the domain. For example, if you're analyzing a 3D case, you may decompose the entire domain, or you may want just to decompose a slice of the domain. When I say slice, I mean you generate, you place a survey plane downstream of the body and use this survey plane to interpolate the CFD data on that plane. And this actually behaves as a real survey plane. In that plane, you will have the wake by any method, XRG far field. In particular, you have the profile drag distribution, which will be afterwards decomposed into wave part and the viscous part. So this operation of generating the slice of the 3D domain is optional, and you can do it inside our filter. And again, it's a BTK operation that is embedded inside the Python code, and as usual, you can modify that to perform some improvements and adapt to your needs. The following step is to read the input array. Basically, the information that has been written by the filter when it's applied to Epsilon aerodata, basically it receives the BTK arrays coming from this filter, so it is internally converted into Python arrays because that's something we can modify and edit. And this information, when it's read inside the Python code, it allows me to perform a breakdown of the flow domain. There are two methods currently coded. The first one is Kusunose, that was the very first method allowing to decompose a profile drag into wave drag and viscous drag, and a recent method based on XRG. This is an example what they show you for, where you have the slice of the 3D domain, and this time by applying either the Kusunose method or XRG, you are able to extract just the wave part at the survey plane that corresponds to the shockwave that appears on the aircraft or the wing. And the output, the last part is just to performing an output, that is to present at the output of the screen the BTK and structured grid that result from this operation of the slice or the entire decomposition. So that's all. It's as simple as that, and all the elements that we discussed in the previous presentation can be observed in the different elements of the interface. So let's go ahead and let's do a practical presentation. Well, for the practical part, I will use an open data that's available on our website. So go to the Epsilon website, open data, CFD data. And then if you scroll down, the second case is a 2D transonic case concerning the airfoil NACA-12 in transonic conditions with zero angle of attack. And this is the case that we're going to analyze. I actually prepared this case in ParaView. I have loaded the case and I have executed Epsilon error data with the corresponding parameters. So as you can see, I have the transonic case here. We can even see if I go to Arn's energy, and I change the scale, let's say 0, 0.1, I can actually see the entire distribution. Energy is basically the entropy generation, and it's a way to visualize the losses that occur inside the wake. So I can see the losses across the shockwave that are provided along the wake of the shockwave in green, and in red I can see the losses that occur inside the viscous region that are provided downstream along the viscous wake. So the main objective is to separate both parts, the green part from the red part, so I can actually have the shockwave drag and the viscous drag separated from the entire profile drag. And that can be achieved by using our specific filter. So make sure that Epsilon error data is applied, and then we will go to this filter, Epsilon Wave Drag. Here in Epsilon Wave Drag, we have first to declare the type of breakdown we want to perform. We can decompose either the entire domain or a slice of the domain. For this first part of the tutorial, I will use the entire domain just to present you the idea. And then you have to perform the breakdown. The breakdown can be made or achieved just one parameter at a time. When I say parameter, basically allows you to select a certain parameter. For example, if I'm here, I'm visualizing, let's say, the total energy, and I want to decompose this field in two parts. I want to separate the part of the shockwave from the part of the viscous part. Here in Epsilon Wave Drag, I have to go here in parameter and select the same parameter I'm visualizing in data. That is, in this case, Arn's energy. And then I have to select the method to decompose. This one is based on Exergy and it's a little bit more robust than the Kusunoso method, so I will stick to this one. Before applying this, I strongly recommend you to apply this option that calls auto apply. By default, it's not activated, so each time you perform a modification, you have to apply by yourself. But in order to take advantage of these slide bars, it's better to apply this option, so it will be applied automatically. So each time I left the mouse, it will automatically apply, so it's easier to change the parameters without clicking on apply each time I modify. So it is quite useful for this option. But remember to deactivate once you left the Epsilon Wave Drag. So use this only for Epsilon Wave Drag. So by default, let these bars all here, the right-hand side. And the idea is to move these bars and progressively the first one and afterward the second bar, and you will see how the green part is being separated from the red part. And this is achieved in the following way. So be sure that you are seeing Epsilon Wave Drag and go here. Here we have the parameter that we want to decompose, and the parameter actually decomposed in two parts, the viscous and the wave part. If I click on parameter, what I'm seeing is here, it's called parameter, but basically it's the one I'm defining here, is Arn's energy. The first thing that you have to do is to put parameter viscous, and parameter wave with the same scale. So here in parameter, I will change the scale. I will put it between 0 and 0.1. so I can see the wake well separated, the viscous from the shockwave part. And I will do the same for the components, parameter viscous between 0, 0.1, and the same for parameter wave between 0 and 0.1. So when I scroll between, this is the input data, as it is from Epsilon aero data, I'm loading this parameter. The output of Epsilon Wave Drag allows me to decompose that into the viscous part and the shockwave part. As you can see, by default, these two quantities are preset as you have a sort of roof decomposition. As you can see, the viscous part takes the boundary layer but part of the wake. In reality, it should take the entirety of this red part. The same happens for the shockwave, that retains the remaining part. It should take only the green part, but as you can see, as it is actually, will contain the red part, which is undesired. What I really want to do is to modify these two threshold values in order that the clipping region will include only the green part for the shockwave and the red part only for the viscous part. So the procedure is quite simple. We start decreasing this slide bar, and you can see as I slide this to the left, the size of the wake increases. The part here in blue increases, advances downstream, basically because it uses a viscous energy generation parameter to tag the cells that lies inside the viscous region. So as you can see, here's a good separation of the green part from what it was the red part. So here it's well extracted, the shock wave. But not here. Here I still have to modify some parameters. So I will let it a bit smaller, like here. Even if you go to the minimum value, it will take everything. So it's not recommendable in this case. You can let it very small, but not the minimum value. So like this, you are extracting very well the shock wave here, but if you scroll outwards, you will see that the wake still contains some part of the viscous region, and that's undesired. What can I do to get rid of that red part? Well, that's why I have the second bar that allows you, if you decrease it, you will see that at some point it starts erasing the internal part, and you can keep moving that to the left until you get all green on the wave parameter. If you go to the viscous part, you will see that it will retain just the viscous part. This, what you can see here, is just a small part of the wake that has been included, and this is because of the mesh. The mesh, as you can see, is not that great. It's not well refined around the wakes, around the shockwave. Sorry. That's why it has some numerical errors. But if you properly refine the shockwave, you will realize that this will disappear, and you will have a perfect separation of the red part from the green part. So this is the input parameter that we will try to decompose. And thanks to these two slide bars, we have managed to decompose it into its viscous part. As you can see, it retains only the viscous part. And the other component is a shockwave. And as you can see, it has retained only the wake of the shockwave. And that's how it works, Epsilon Wave Drag. Well, at this point, we just had covered one of the options of Epsilon Wave Drag that concerns the breakdown of the entire domain, but there is another option that is slice of the domain. So if you select that, basically what it does is to generate a slice plane. By default, this slice plane is normal to the upstream direction, but you can change direction as you want by defining the normal of the survey plane. I let it die by normal by default. That works always fine. And then I have to define the position of the survey plane. By default, it's at the origin, but in my case, I want to put the survey plane downstream of the body. I will put that, let's say, 0.5 meters. And what it does is to take the entire domain generated by Epsilon data, that is the entire flow field. Then it generates a slice that gives me this line corresponding to the survey plane. And all along this line, it will take the parameter that I want to decompose. In my case, it's the energy. And then, for this line, it decomposes this parameter into two components, the viscous and wave parts. If you visualize just the data of this slice, I will hide our data for a while, you will see that parameter is as it is, just a slice of the input data, and it has been decomposed into this viscous part. You can see it retains just the red part, and the wave concerning the green part. Here you might ask, what's the interest of doing this such a decomposition for a 2D case? Well, for 2D case, it's quite interesting for observing the distribution of a given parameter, because Epsilon Wave Drag applied to slice of the domain will give me a distribution all along this line, so all along the survey plane, so I can visualize that. So let's go for it. I will click here, I will apply filters, alphabetical, work by scalar, and I will basically deform this line based on the magnitude of the energy at each point. In my case, I will deform this line to the right-hand side all along the x-axis, so I define x-axis as a warp deformation. As you can see, it starts being deformated. Let me change the color so we can see that better, and even you can increase the width of the line, let's say like this. Okay, you can see that better. I will reduce the scale factor. Okay, so basically what I have is here the survey line that has been generated by Epsilon Wave Drag. And all along this line, I have this distribution of the parameter that I want to decompose, that's in my case energy. And this has been decomposed into two parts. One part is the viscous part, that you can see it retains just the distribution inside the red part. And you can also visualize the distribution all along the shockwave. So you have the distribution of both parameters already separated, which is quite useful for physical analysis. For the last part of this tutorial, I will use a 3D transonic case that you can actually download in our website. Just go to our website, tab Open Data, CFD Data, and then you scroll down just to the bottom, and you'll find this case, a 3D transonic case of a rectangular wing, and this is the case that we will study right now. I have actually downloaded, I execute Epsilon near field to extract the surface, and I have visualized the shock wave by using a contour of a shock detector of value 1.1. You can do that by yourself. Now we will just tackle the use of Epsilon Wave Drag to extract the wave component. So let's go to Epsilon Aero Data. Let's do it the element active and click on Epsilon Wave Drag. As before, the first thing that we have to define is the breakdown. I want to break down just a slice of the domain for 3D cases. That's the recommended approach. Even if you really want to decompose the entire domain, I strongly recommend you to start with the slice because that's faster. Once you have properly set up all these parameters, you can go back to the entire domain. So let's get started with the slice of the domain. And as before, you can define the normal of the survey plane, and you have to define the position of the survey plane. I will place that, let's say, 1 chord downstream, roughly. And when you apply, you will see that the survey plane appears. The survey plane generates a slice on the entire domain. This is the entire CFD domain. And this is a slice of the domain that corresponds to the survey plane that has been generated downstream of the body. And in this plane, you can actually see some parameters. The parameter that I want to decompose, I have to select it. Here in parameter, you have to select the parameter that you want to decompose. In my case, as before, I will select the energy. That's the generation of losses, the generation of entropy. And if you apply here in parameter, you will see, as before, in red, the part corresponding of the wake to the viscous part, and in green, the part of the wake corresponding to the shock wave. So our objective is to decompose that. So as before, we will achieve that by using either of these two methods and by sliding this slide bar. So I will activate again the auto apply, and I will start reducing this until the two viscous and wave are properly separated. The first step, of course, is to come here on parameter and change the scale. 001 from parameter is okay, viscous still 001 okay, and wave are the same range. So these three parameters, the original input and its decomposition. The three have the same scale, so I can easily visualize if the decomposition is going right or not. So now that everything is ready, I can start sliding this downwards, and I will visualize just the wave component in my case. So I start sliding it, and I will see that at some point it may disappear, or not. You'll see start cropping here, just very small values. Here's the entire wake in red, and now if I decrease, I start seeing that the wake is actually decreasing. I can maybe put that by hand. And you can see that here we have a red line in the middle of the viscous part, and we can get rid of that by decreasing the second slide bar. And okay, just a little bit more. And now we have get rid of almost everything. Yes, we have separated the green part corresponding to the shockwave from the viscous part that's here. And that's how you perform a decomposition of a given parameter at the survey plane into components, its viscous part and its wave part. For the case of breakdown, the slice of the domain, once you achieve your decomposition, you will also have here the integrated values. That is, parameter has a density here. So this is what you're seeing is the distribution on the plane of the density of energy at each point. If you integrate this parameter on the entire surface, you will have the total energy that is flowing out of this survey plane. This quantity is being integrated for the case of slice of domain, and the result of the integral is here. You can see parameter integrated gives you 244 drag counts. And once this decomposition has been properly set up, you have the decomposed values. You have viscous part, 136 drag counts, almost 100 drag counts of shockwave. And the same, of course, will happen for the 2D case. If in 2D case you apply the slice of the domain, you will have the viscous part separated from the wake part as well as the total quantity. And for the 3D case, once you are happy with this decomposition at the plane, you can decompose the entire domain simply changing here to the entire domain. It will take just a bit more time because it will decompose the entire domain, but you can do that. It will take just some minutes to compute that. And this concludes this demonstration of Epsilon Wave Drag.